Okay, hello everyone. So today we are going to talk about second law of thermodynamics. Previously, we already have discussed about first law of thermodynamics, and we found that first law of thermodynamics basically describes about the conservation of energy. But first law of thermodynamics is failed to describe the direction of flow of heat. So to fulfill that inadequacy, the second law of thermodynamics come in play, and it clearly describes how the heat energy flows. So sometimes the heat energy flows from higher temperature to lower temperature. Sometimes the heat energy can be made to flow from low temperature to higher temperature. So this flow of heat energy, how it is possible to do, or how the heat energy being transferred from one state to another, one temperature to another, is clearly described by second law of thermodynamics. So in this lecture, basically we will be discussing about the general idea of second law of thermodynamics. Then we will be following up it with the general working mechanism of different kinds of engine and the heat pump, that is refrigerator, and we will be following up finally with some old questions of different institutions entrance examination like IOE, IOM, KU, MOE, and all this. Okay, so let us begin the general discussion. So this second law of thermodynamics, as I already mentioned, this describes basically about the heat flow. How does the heat energy flows from one body to another, and how the conservation law of energy is being satisfied by the heat engine or refrigerator. So to explain this, two renowned scientists, Kelvin and Clausius, gave their statement. And firstly, the Kelvin statement suggests that we cannot obtain the continuous work from a body uh, cooling to the lower temperature than the surrounding. It means that we cannot obtain work without rejecting heat. So Kelvin statement suggests that without rejecting heat. Okay, so without rejecting heat, without rejecting heat. Okay, without rejecting heat, the machine does not work. Without rejecting heat, machine doesn't work. Okay, does not work. So this is the general statement of Kelvin. And similarly, the second law of thermodynamics was also described by the another famous scientist called Clausius, and he also suggests that the heat energy cannot be transformed from lower temperature to higher temperature without uh, external agency, without aid of external agency. This means that we cannot make a transfer of heat without doing work from lower temperature to higher temperature. In another language, what we can do is doing work, doing work on doing work by external agency. Okay, we external agency. Okay, so doing work through external agency on working substance, on working substance, we can transfer heat from lower temperature to heat transfer from lower temperature to heat transfer from lower temperature to higher temperature. Okay, so low temperature to high temperature. Okay, something is wrong with this one. So low temperature to high temperature. So this is how we can transfer the heat, low temperature to high temperature. High temperature. So this is the general idea about the second law of thermodynamics. And basically here we will be talking about the working mechanism of a different engine. So first of all, Carnot tried to describe the working of a heat engine, and for that he considered a very simplified type of engine that we basically call Carnot engine. Carnot engine. In this engine, the work will be done in a cycle, and it tried to figure out whether the efficiency of a heat engine will be 100% or not. And basically in this Carnot engine there will be uh, and four different kind of components. So basically we call the first component is source. Okay, so let me tell you one thing about this source that could be helpful in you during the time of examination. So source चाहिँ कस्तो खालको लिन सकिन्छ भने whose temperature is very high. Okay, temperature is high, and we believe this kind of source has infinite heat reservoir. Okay, infinite heat reservoir. It is infinite heat reservoir, and even we can call this is provided with infinite specific heat capacity. Okay, is infinite specific heat capacity means uh, the temperature of the source will not change appreciably even after taking large amount of heat energy. Such kind of ideal source has been taken in case of Carnot engine and Carnot cycle. Okay, so source always be at higher temperature, and it will reserve very large amount of heat energy. And then another important thing comes here is your sink. Okay, so in the same way how we have considered the source, the same manner sink will be the reservoir at low temperature. Okay, this of low temperature. Okay, so low temperature. So also believe that it is infinite heat reservoir. Okay, and its specific heat capacity is very high. Specific capacity is infinite. Okay, so if you reject some amount of heat energy to this sink, then the temperature of the sink does not change appreciably. Such kind of ideal type of sink will be considered. And the third part is your working substance. Working substance. So working substance is something that takes the heat from the source and does some work, and let's say it takes heat energy from the source and does some work, mechanical work, and it transfers the heat energy to the sink. Certain amount of heat energy will be transferred to the sink. Such kind of material is called working substance. And to make the working possible, we require cylinder. In case of this ideal Carnot engine, the cylinder is taken to be perfectly insulating and provided with massless, frictionless piston, which can move easily top and bottom, or it undergoes expansion and contraction without any frictional force between the layers. So such kind of ideal type of uh, Carnot engine system will be taken, and if you observe the Carnot cycle, then Carnot cycle looks like this in our PV diagram, and from this PV diagram we can figure out the total work done, and finally we can calculate the efficiency of the system too. Okay, let us suppose the system begins from this and it undergoes isothermal expansion, and it will continue for adiabatic expansion, and then it come back to adiabatic compression, and finally it goes to isothermal. Okay, this is isothermal expansion. Okay, this one is isothermal expansion, and then it undergoes adiabatic expansion. This is isothermal contraction, and finally this is your adiabatic contraction. So if it undergoes this cycle, so from P1V1 to P2V2, okay, P2V2, and then it goes to P3B3, and this is P4V4, okay, P4V4, and finally from P4V4 it reaches the P1V1. So this is how it completes the cycle. So particularly in this case, the heat energy will be absorbed. Okay, so this is the situation where the heat energy will be taken, and at constant temperature the gas will be expanded. Okay, and after that the further expansion of the gas will be taking place without rejecting heat or without receiving it. That's why the gas or the working substance or the material will be expanding adiabatically in cost of the internal energy. That's why certain temperature will be found to be decreased from this first isotherm to second isotherm. So if it is your temperature T1, then this is gonna be temperature T2, because some amount of work is done in cost of this internal energy. That's why the work will be, so the temperature of this will be smaller than the previous one. And finally in here, so if the further contraction will be taking place at uh, adiabatic condition, then again the work will be done against of gas. That's why temperature of the gas or working substance will be increased, and finally it will reach the state of P1 and V1. Okay, so in here certain amount of heat energy is rejected to the sink. Okay, that's why it come back to the original state. So if we see the total work in its case, we can find that certain amount of work is done on gas. Okay, so this is, let's say, W1. This is positive because this expansion. This is W2, this is again expansion, and this one is W3, and this one is W4. See, the work is being done between this W2 and W4 are equal and opposite. This is expansion and this is contraction without changing the heat. That's why they are equal to one each other. So the net amount of work done will be calculated from this W1 and W2, and we can obtain the efficiency. So if we calculate the efficiency of the system, then we can find that the efficiency of the system will be given by the total work done divided by total heat taken from the system. Okay, so if Q1 is a heat taken from the system and Q2 is rejected to the system, then the difference of these two heat will be giving the amount of work done. So if we simplify, then we can find the efficiency will be Q2 by Q1. Okay, so if you wish to write in terms of percentage, then you can simply multiply by 100%. See here, we know that from this Kelvin statement, without rejecting heat, the heat engine cannot work. So if you just recall this statement, then you can find that without rejecting heat, the machine cannot work. That means Q2 is not zero. So if Q2 is not zero, then this quantity is not 0. Okay, so as this quantity is not 0, this overall quantity will always be less than 1. So this quantity will always be less than 1. That's why we can say that the efficiency of Carnot engine is also less than 100%. Okay, so this is how the Carnot cycle works, and the amount of work done in Carnot cycle can also be calculated mathematically by using the concept of work done in isothermal process, work done in adiabatic process, you know well. So in this isothermal process, PV equal to nRT. Okay, so in here the the work done will be calculated as nr by gamma minus 1 T1 minus T2. Similarly in here, so T2 minus T1. Okay, so if you just calculate the work done in this case, in this case, in this case, and this one, this will be equal and opposite. And if you find the total work done W1 and W2, and if you rearrange all the parts, then finally we will be finding out the magnitude of the work done to be like this. Okay, let me just write in here. So the total work done in the system, okay, can be written as W equals to so the overall work done can be written as, okay, so here we can write W equals to the work done in here W2, sorry, this work done is W1 minus, okay, W3. So this is the work done, total work done by the system. Okay, so this is the idea of a Carnot engine. Okay, so if we simplify this Q1, Q2 in terms of temperature, then the efficiency of the engine can also be obtained as 1 minus T2 by 1 minus T2 by T1. Okay, you can just simplify heat energy in terms of temperature as well. Okay, so T1, and again from here, so if you want to express in terms of percentage, then you can multiply it with 100%. Okay, 100%. So the temperature of T2 is not less, or T2 is not 0. Okay, so if it is not 0, then this quantity T2 by T1 is something positive. And if you subtract something positive from 1, then obviously the overall quantity will be less than 100% or less than 1. So this is the general idea about the Carnot engine. So now let us move on to discuss about two different kind of engine that we are gonna look at in our discussion as well. And that is, these two engines are petrol engine and diesel engine. Okay. Okay, so we will be talking about in here the petrol engine and diesel engine. So if we just look this engine from a PV diagram, it will be quite easier. That's why I'm just drawing the PV diagram for this petrol engine, as well as I will be talking about diesel engine finally in next discussion. And the meantime, let me just make a quick comparison between this diesel engine and petrol engine, and you can easily compare the efficiency as well. So in case of petrol engine, the um, the engine will be working on 4 strokes. Okay, that's why sometimes this diesel engine and petrol engine also be called as 4-stroke engine. So let us suppose this is atmospheric pressure P0. Okay, so in petrol engine, the gas will be absorbed at constant at atmospheric pressure, and gradually the piston will be expanded. Okay, so first of all, what happens is piston will be expanded on the, and all the gas will be entered inside the chamber of this piston. For example, let's say this is your piston system cylinder, and in here is your piston. If the crank wheel moves down, then the inlet valve will open. Why the gas will come in here from the atmosphere is, as the piston goes down, partial vacuum will be created. So this, as the partial vacuum is created, your inlet valve will open, and atmospheric gas will be passed to this uh, partially vacuum like a chamber. And what happens is, as the crank wheel continues to move, all the gas that has been injected inside the cylinder starts to compress. So the gas will be compressed in cylinder. So यहाँबाट हेर्ने हो भने सिलिन्डर भित्र ग्यास यसरी कम्प्रेसन हुँदै जान्छ। यो स्टेटमा पुगिसकेपछि अब हामीलाई थाहा छ यो हाम्रो पेट्रोल इन्जिनमा हाम्रो सोर्सेसहरु चाहिँ के हो भन्दा वर्किङ सब्स्टेन्स के हो भन्दा 2% of petrol and 98% of atmospheric air will be used. And you know well, petrol is volatile in nature. So normal temperature में यो के हुन्छ gaseous state मा हुन्छ. That's why यसको mixture चाहिँ हाम्रो के भयो त working substance जस्तो भयो. Okay? So यो working substance भयो. So यति यो volatile mixture of petrol and 98% of air will come inside here. So the mixing of this substance will be taking place outside the chamber. यो बाहिर गरिन्छ र जब यो सिलिन्डर भित्र आउँछ सिलिन्डर भित्र आइसकेपछि यो कम्प्रेस हुन थाल्छ। कम्प्रेस हुँदै जाँदा यो भोल्युममा आइपुग्छ। यो भोल्युममा आइपुगेको सब्स्टेन्समा अब यहाँबाट इग्निसन सुरु हुन्छ। यहाँबाट हाम्रो स्पार्क प्लगले स्पार्क प्रोड्युस गर्छ र स्पार्क प्रोड्युस हुँदाखेरि त्यो बेलासम्ममा यसको भोल्युम चाहिँ कन्स्टेन्ट नै रहन्छ भने प्रेसर बढ्छ। सो स्पार्कले के गर्दिने भयो यहाँनेरि Q1 हिट एनर्जी निकाल्दिने भयो। सो अब यहाँ भोल्युम पनि बढ्छ र यसको टेम्परेचर पनि बढ्छ। अब यो स्टेटमा आइपुग्छ। फेरि के हुन्छ त as the heat energy is being supplied अब यो heat energy ले यो pistonलाई push गर्छ। That's why the expansion will be taking place. This is how the expansion will take place, and reaching this pressure again the outlet valve will open. So this outlet valve will be opening and all the gas will be skipped out to the sink, that is our surrounding at atmospheric pressure level, this one. So this is how the engine cycle of engine will be completed. So in petrol engine, heat will be taken from this one and the expansion will be taking place, and this expansion is basically called, or this zone is basically called power stroke. Okay, in this situation the engine will get power stroke. Okay, out of 4 strokes. So intaking and then getting energy from the source and then expanding and finally rejecting the exhaust gas to the surrounding. So 4 strokes मा यो काम हुन्छ। त्यसैले 4 strokes engine पनि भन्न पाइयो। अब यतापट्टि हाम्रो डिजेल इंजिन को कुरा गर्ने हो भने प्रोसेस अलमोस्ट सिमिलर छ। So मानौ यो हाम्रो एटमोस्फेरिक प्रेसर हो भने जब यो पिस्टन, लेट अस सपोज दिस इज आवर पिस्टन, यो पिस्टन जब यता मुभ गर्छ यहाँ पार्शियली भ्याक्युम क्रिएट हुन्छ र द ग्यास atmospheric gas, pure gas will be coming inside the chamber at atmospheric pressure level. Okay, so suppose all the gas is reached inside, as the crank wheel goes down partial vacuum will be created and gas will come inside in this chamber. अब यसपछि जब यो crank wheel further inertia of motion ले माथितिर जान थाल्छ अब यो contraction हुन थाल्छ। यसरी contraction भयो। यो contraction भइसकेपछि यसको पेट्रोलको र डिजेलको केसमा एकदमै सिग्निफिकेन्ट डिफरेन्स कहाँ आउँछ भने the compression in case of petrol engine is very low. Okay, so temperature increase is very low. यसमा temperature in the order of 1000 or generally 600 to 700 यस्तो पनि किताबहरुमा भेटिन्छ। So I just wrote here in terms of 1000 Kelvin जस्तो हुन्छ भने यसमा compression एकदमै हाई हुन्छ, extremely high compression हुने भएको हुनाले यो केसमा टेम्परेचर चाहिँ झन्डै यो अब पिस्टन माथि जाँदा यसको भोल्युम अलमोस्ट 1/18 or 1/20 जस्तो हुन्छ है। सो V2 by V1 लिने फाइनल भोल्युम बाइ इनिशियल भोल्युम लिने हो भने इट कुड बी लाइक 20 or so. सो यो यति सानो भोल्युममा कम्प्रेस हुन्छ कि ग्यास कि यसको टेम्परेचर अलमोस्ट 2000 केल्भिन को अर्डर में पुग्छ। सो यो टेम्परेचर में पुग्ने बित्तिकै यहाँको यो सोर्स फ्यूल ओके डिजल diesel को spray चाहिँ यहाँबाट गरिन्छ. So once the diesel will be sprayed at this high temperature at constant pressure, okay, so यहाँबाट heat energy हामी in गर्छौं in the form of petrol spray. So यति high temperature मा petrol आफै burn हुन थाल्छ र burn भइसकेपछि further expansion will be taking place and the engine will continue to expand, and in this situation all the power will be received by the engine. So this is your power stroke. And finally, as the piston will move down the way and finally reaches this pressure, the outlet valve open by itself and all the exhaust gas will be rejected. So Q2 will be rejected, and again the system goes to its one initial pressure level, okay, and finally continue to another cycle. So this is how diesel engine and petrol engine works. So the fundamental difference between these two engines is यो लो टेम्परेचरमा काम पनि गर्छ, यो यसको पिस्टन भित्रको टेम्परेचर एकदमै ज्यादा हुन्छ. यसमा कम्प्रेसन रेशियो एकदमै सानो हुन्छ. कम्प्रेसन रेशियो सानो भएको हुनाले हामीलाई स्पार्क चाहिन्छ, अनि यसमा कम्प्रेसन रेशियो हाई हुँदा टेम्परेचर हाई हुन्छ र यसमा इग्निसन चाहिँदैन है. यो आफै इग्नाइट हुन्छ, यो आफै ब्लास्टिङ हुन्छ जुन बेला यहाँनेरि हामीले पेट्रोल स्प्रे गरिदिन्छ. यो इन्जिन रिलेटिभली लाइट हुन्छ है, यो रिलेटिभली लाइट हुन्छ. हामीले इग्नाइट गर्नुपर्ने हुँदा ब्लास्टिङ गरिराख्नु परेन, त्यसैले यो इन्जिन लाइट हुन्छ भने यो डिजल इन्जिन चाहिँ एकदमै हेभी हुन्छ. त्यसैले डिजल इन्जिन चलाउनु छ भने त्यो भेहिकलको मास पनि बढी चाहिन्छ, अदरवाइज त्यो भाइब्रेसन बढी गर्छ है. सो यो लाइट भेहिकलहरुको लागि बढी युजफुल हुन्छ भने यो हेभी भेहिकलहरुको लागि युजफुल हुन्छ. यसमा कम्प्रेसन रेशियो लो छ, V2 by V1 लो भएको हुनाले इफिसियन्सी लेस हुन्छ भने यसको चाहिँ इफिसियन्सी हाई हुन्छ. Okay, so this is the key difference between this petrol engine and heat engine. No matter जुनसुकै इन्जिन युज गरौँ तर यिनीहरुको somehow the working mechanism is similar. Working substance ले heat energy receive गर्ने, त्यसपछि expansion हुने, त्यो जब सिलिन्डर एक्सप्यान्ड हुन्छ, सरी पिस्टन सिलिन्डर भित्र एक्सप्यान्ड हुन्छ, त्यो एक्सप्यान्ड भएको केसमा तिनीहरुले पावर गेन गर्छन् र त्यही पावरले हाम्रो इन्जिनहरुलाई रन गर्छ. Okay, this is the fundamental idea of this petrol engine, diesel engine and petrol engine. Okay, now let me move on to figure out the efficiency of this kind of engine can also sometimes be written as efficiency as in terms of volume. Okay, so efficiency will be like as a 1 minus 1 by rho. Okay, so this rho is the ratio of compression, this one. Okay, compression ratio to the power gamma minus 1. So this gamma is the constant. Okay, BC P by CV. Okay, this is what gamma. So from this expression also we can figure out the efficiency of engine. And if you just look at the rho is in denominator. Okay, so just को compression ratio एकदमै ज्यादा हुने वाला छ, त्यसको efficiency पनि ठुलो हुनेछ. In V2 by V1 यहाँनेरि आउँछ. Okay, so I just discussed about this petrol engine and diesel engine in brief way. Now I like to bring you here to some previous year's questions. Okay, so let me bring you to the okay, you can see some previous year questions from second law of thermodynamics. मैले अगाडिको लेक्चरमा फर्स्ट ल अफ थर्मोडायनामिक्स सँग रिलेटेड सबै प्रिभियस इयर्स को क्वेशनहरु डिस्कस गरिसकेको छु. सो सेकेन्ड ल अफ थर्मोडायनामिक्स सँग एसोसिएट भएको रिलेटिभली लेस नम्बर अफ क्वेशन्सहरु छन्. सो आई एम गोइङ टु टक अबाउट दिस क्वेशन्स इन हियर. ओके, सो रेफ्रिजरेटर ट्रान्सफर एभरेज हीट एनर्जी दिस फ्रम -10 to 25. The average power consumed by the refrigerator. हामीलाई थाहा छ रेफ्रिजरेटरले के गर्छ भने Q2 heat plus certain amount of external agency बाट एनर्जी पाएपछि कहाँ लान्छ, Q1 मा लान्छ, राइट. सो यही आइडियाको आधारमा हामी यसलाई चाहिने पावर हामी निकाल्छौं. ओके, सो लेट मी जस्ट क्याल्कुलेट. वी आर गिवन दिस टेम्परेचर T1, दिस टेम्परेचर T2. ओके, दुईटै टेम्परेचर हामीलाई दिएको छ. भने इनरमा भएको Q1 र Q2 आरामले निकाल्न सक्छौं। हामीलाई थाहा छ Q1 by Q2 को रेशियो, okay, efficiency is the same हुन्छ, Q1 by Q2 will be equal to T1 by T2, but you should not forget one thing, that your temperature must be in Kelvin. So if you just do this mathematics, यसले कन्ज्युम गरेको एनर्जी चाहिँ, okay, has to transfer 263 joule. यो 263 joule Q2 हो, okay, Q2 भएको हुनाले अब हामी कति लेख्न सक्छौं भने कति हिट एनर्जी चाहिँ बाहिर फाल्छ त यसले भनेको, बाहिर फाल्ने हिट एनर्जी भनेको 263 प्लस एक्सटर्नल एजेन्सीले गर्ने वर्क हो है। सो यो Q2 अब यहाँ सब्स्टिट्युट गरौँ। सो Q1 बाहिरको सराउन्डिङ को यहाँनेरि 263, ओके, यसलाई केल्भिन स्केलमा निकाल्ने हो भने 10 र 25 you can easily do by adding 273, that is 298 and 263, I believe, okay, 263, and if you just subtract, sorry, if you just simplify this, then you are going to get Q1 in the order of, I believe, बढी नै हुन्छ। सो यसको भ्यालु हुन्छ, okay, 263 cancel out, Q1 will be equals to 298. You can find, see, 298 चाहिँ Q1 हुँदो रहेछ, इन्भाइरोमेन्टमा फ्याक्ने टोटल एनर्जी चाहिँ 298। सो 298 बाहिर फ्याक्नु छ, त्यो मध्ये 263 कहाँबाट लिएको छ, सिङ्कबाट, भने एक्स्ट्रा एनर्जी कहाँबाट लिन्छ त, एक्सटर्नल एजेन्सीबाट। त्यो एक्सटर्नल एजेन्सी यहाँ जति डिफरेन्स छ त्यही डिफरेन्स हो। सो 298 minus 263 गर्ने भने I believe this is 35, okay, so our correct answer is going to be 35 watt or 35 joule per second, okay. So I want to clear this frame and I will be doing the another problem, okay. You can do this kind of question so easily. Now next problem is the efficiency of engine working between 27 and 273. I believe this is very easy question for you. So efficiency of the engine can easily be calculated by the simple formula 1 minus T2 by T1, okay. So if you just do that, so your efficiency for this 27 and 127 is I believe 25%, okay. So if you can simply do this kind of mathematics, let me just do there so that you can do it. Like efficiency is 1 minus T2. T2 means 27 plus 273, okay, divided by 127 plus 273. If you just do this mathematics, then you can easily get the value of eta, I believe 25%, okay. So further another question is there, the efficiency of Carnot engine is 1/5, okay. Initially it was 1/5 and the temperature of the sink is lowered by 45 degrees C. So 45 degrees C भने पनि 45 degree Kelvin भने पनि डिफरेन्स अफ टेम्परेचर हो, यसले खासै फरक पार्दैन। त्यसैले 45 केल्भिन भयो भने डराउनु पर्दैन यहाँनिर। र इफिसियन्सी कति हुन्छ 1/5। त्यसो भए इनिशियली यो सिङ्कको टेम्परेचर के थियो भनेर सोधेको छ, यसलाई पनि म सिम्पली सर्टकट सिकाइदिन्छु। सो यहाँनिर हेरौँ। सो इनिशियल स्टेटको सिम्पली फर्मुला लगाउँ। इफिसियन्सी कति दिएको छ, दिस इज योर 1/5। सो 1/5 इक्वल्स टु 1 minus T2 by your T2 sinko T2 by T1. So if you just calculate this T2 by T1, let me use another color so that you can distinguish. So initial T2 by T1, okay. So your T2 by T1 is going to be equal to 1 by, so this one be positive, so 1 minus 1 by 5. So this is your 4/5. यहाँबाट हामी इजिली निकाल्न सक्छौं। This is 4/5, that is T2 by T1, okay. T2 by T1, the value of T2 by T1 will be like this one. Okay. Now हामीले अब गर्नुपर्ने के चाहिँ भने 45 डिग्री दुईटैबाट सबट्र्याक्ट गर्नु पर्यो र के होस् हाम्रो सेकेन्ड भ्यालु चाहिँ ओके द सेकेन्ड इफिसियन्सी वुड बी 1/3 T2 by T1 को भ्यालु कति आयो 4/5 ओके जस्ट रिमेम्बर दिस एन्ड अब के हुन्छ इफिसियन्सी चाहिँ 1/3 हुन्छ त्यो बेला के गर्नु पर्यो T2 भनेको initial T2 minus 45 okay so we have lowered the temperature of sink by 45 okay so हामीले सोर्स को बारेमा त केही भनेका छैनौं सोर्स को बारेमा केही भनेको छैन भने the temperature of the source is same so this is T2 minus 45 divided by T1 okay अब हामीलाई थाहा छ T2 यो नयाँ टेम्परेचर हो okay I just forgot to write here 1 minus okay so T2 minus 45 by T1 is 1/3 so T2 by T1 को भ्यालु हामीलाई थाहा छ है T2 by T1 को भ्यालु थाहा छ so 45 by T1 को भ्यालु हामी निकाल्न सक्छौं so from this equation you can easily calculate the value of T1 once you get the value of T1 and using the efficiency this 1/5 you can easily and directly can find the value of T2 original T2 and if you just simplify this I have done this shortcut mathematics and obtained you is the value of sink is 270 okay I believe in here there is a answer 270 Kelvin okay so the is next the specific heat capacity of ideal gas under isothermal condition okay so isothermal condition मा चाहिँ के हुन्छ होला let us figure out isothermal condition मा temperature constant हुने रहेछ okay specific heat capacity जेसुकै होस् हामीलाई थाहा छ specific heat capacity भनेको Q by ms dt if dt itself is 0 if dt is 0 then specific heat capacity is going to be infinite okay so this is so simple to do another question is there the ratio of slope of PV graph of adiabatic and isothermal process I believe you know well okay the slope of this adiabatic is gamma times more okay slope okay let me just write slope of adiabatic okay, let me just write this way slope of adiabatic will be gamma times the slope of okay so it is a bit difficult to write in here the slope of isothermal okay the slope of isothermal so you can just see here we have to calculate the ratio of adiabatic to isothermal so for this adiabatic to isothermal will be gamma adiabatic divided by isothermal will be simply adiabatic divided by isothermal so this is going to be equal to gamma okay so the ratio is going to be gamma right so the answer is in here next the efficiency of Carnot engine depends on nature of the fuel use nature of the working substance temperature of the source and sink and all okay so हामीलाई थाहा छ कुनै पनि हिट इन्जिनको इफिसियन्सी चाहिँ यो कुनै कुरामा डिपेन्ड गर्दैन सिम्पली डिफरेन्स अफ टेम्परेचर बिट्विन सोर्स एन्ड सिङ्क हुन्छ है त्यसैले टेम्परेचर अफ सोर्स एन्ड सिङ्क एकदमै भ्यारिड छ भने त्यसको इफिसियन्सी ज्यादा हुन्छ त्यसैले हामी जहिले पनि के गर्न खोज्छौँ भने इफिसियन्सी बढाउनु छ भने द टेम्परेचर अफ सोर्स एन्ड सिङ्क शुड बी so different so that's why the answer is going to be this one and which of the following relation is correct for efficiency of engine so in just discussion I told you the value of this efficiency will be written in the form of this 1 minus 1 by This rho means V2 by V1. Okay, V2 by V1, that is compression ratio. We all know this compression ratio, and this is gamma minus 1. Okay, so the value of gamma minus 1 is that. That's why the correct answer is this one. Okay, so in this discussion, I basically discussed about the second law of thermodynamics and the questions from previous year. So I believe you got the general idea of this all. So follow us and keep us updating what kind of topic you are looking for MCQ. Thank you all.